Is a graphing calculator file that you could download that is referenced in, I think it's reflection number 3. So that's there. So when you see open this file, it is there on Blackboard for you to do that. And the document that I posted goes way beyond our current place in the course. So hopefully for those of you who are looking for, being able to look ahead a little bit, you can do that now. So that's that long document. Don't be intimidated by it. We're going to parse through it, but so the first 5 pages for Friday, but you can sort of look ahead if you want. My math lab is coming up in about 1.5 to 2 weeks or so. So if you haven't already registered for that, you can start thinking about it. Right? It will be coming. And then also I wrote up some solutions to the homework that was due today, so you'll start seeing some homework solutions online this afternoon, okay? So hopefully that'll help you guys with your studying for quizzes and tests, and you can get the kind of feedback that you're hoping for. Okay, so, yay. Okay, so today we're going to keep talking about the big picture, and then along with it, all the tiny little details, okay? So last time I didn't have this animated, now it's animated. We were talking about a rubber ball being pushed down and then moving up and down and having its rate function, its exact rate function. So I can model the velocity of this ball as it's moving away, away and then back towards this plank up at the top of the screen. With this exact function. So at any given moment in time, right, since the animation starts, I can say, oh, at this moment in time, the velocity of the ball has this y value, okay? But, chances are I'm probably interested in something else about this scenario. In particular, I might be interested in how far has the ball traveled during this animation, okay? So as soon as I ask that question, now I'm trying to do something else, okay? I'm trying to take a velocity and turn it into an accumulated distance, okay? So the way in which we don't have a way to do that directly from this type of function. We have no direct route at the moment for going from exact rate to exact accumulation. So our tool is going to be to turn this exact rate function into a pretend rate function, an approximate rate function, okay? So how do we do that? We partition the x-axis into little chunks, so little bits of change in time, and then we make a step function according to those little chunks and using the exact rate function. So I've got little chunks of time that I've partitioned, and then I've found the corresponding rates by using the exact rate function at the left endpoint of each interval, okay? And so once I have that kind of information, well, let's forget about the original rate of change function for now. Now I've got a step function, a piecewise constant rate of change function. This is beautiful because now I can talk about little bits of accumulation, little bits of distance, right? So at the very beginning of this animation, the ball is standing still, right? So it's traveled nowhere. Nothing has happened, okay? But as I let the animation go for just a little bit of time, so I think I've divided this up into, what, like 0.2 of a second? Okay, so right here, this is 0.2 of a second. So if I want to figure out how far has the ball traveled in that little bit of time, I can say, well, the little bit of change in distance is gotten by the rate times that little change in time. So this is, the actual rate at the left end of the first interval times the change in time at the first interval, okay? And then, so, okay, well, why is that helpful? Well, because then I could say the distance, at the total distance at the end of that interval is the starting distance plus the little bit of change, Okay, so total distance is the starting distance plus a little bit of change. And then I could do it again. The next 0.2 of a second, the rate that we got from our constant rate of change rate function was approximately 0.98. So over the 2-second interval, I've got this little bit of change. So then I could get the total distance by saying, oh, well, that's going to be the little bit of change that I've already accumulated, right? So that's what this 0.2 is, plus the extra little bit that comes from doing this computation. And then we could do it again and again. All of these little bits accumulating to give us a total amount of accumulation. That's the big picture, okay? That's what we're trying to achieve right now, okay? But, I mean, there's some stuff that I did here, right? Some fancy things. So let's talk about how I got it, right? So the really tricky part of doing this process is defining our pretend rate of change function, okay? Our piecewise constant rate of change function. So how do we go about doing that? Well, we start by partitioning the x-axis into intervals of length delta x. Then we reassign all x values in a given interval to the x value at the left end of that interval. Okay? I'm going to break these down, so try to just stay with me, okay? And then we define the step function as a piecewise constant function where the value in each interval is the actual rate at the x value found in number 2. Okay, so that's a lot. We're going to break it down step by step. Okay, luckily the first step is easy. Okay, so this is what we were doing at the end of class on Monday. Okay, we divide the x-axis into intervals of length delta x. So in this picture, I've got a starting value, which was a equals -1. So because the number line is infinite, right? The x-axis goes infinitely forever in both directions. So I have to pick a place to start. So I'm going to start at -1, and then I'm going to partition my x-axis into intervals of length delta x, which we've set to be 0.8. Okay, and then I can just continue doing that to the right. Okay, so that's how we start. Now is where the magic happens. Okay, so what we want, our end goal is to have this constant rate of change function, piecewise constant rate of change function, that has the values of the rate at the left end of every interval. Okay, well, that means I need to focus on the left end of every interval. And the way that we're going to do that is we're going to reassign current x values to the x value at the left end. Okay, so in this case, I've got a current x value of 5.16, and I want to reassign this x value to the x value at the left end of the interval it's in. Okay, so far so good? So anytime I can give you something and get something spit back out, what type of thing am I trying to define? A function, okay? So at the moment, my goal is a function that takes current x value and outputs another x value, but a very special x value, right? Outputs another x value. So this is a little different than functions that we're used to, right? Because normally you put in an x, you get out a y. That's not what's happening here, right? So we're putting in the current x value and we're outputting another x value, which is the left endpoint of current interval, okay? So when I say current interval, I'm talking about the interval containing the current x value, okay? The first word is goal and then function, okay? So we kind of thought a little bit about how to do this, but it was a little rushed. So let's sort of think about it again. I'm talking a lot. that okay? Shoot. I was hoping you'd say no. You want to talk. Okay, so how are we going to do this? Well, the most sort of intuitive way, at least in my mind, is to think, okay, I'm starting here, and I want to get to here, right? This is my goal. So I have a starting value, and I've conveniently partitioned lengths along my x-axis. Oh, that was cool. Okay, so I have a starting value. So let's see, my left endpoint, I could think of getting it by taking my starting value, right, and adding what? The lengths, like sort of, I want to add the distance between the starting value and the ending value, right? Because that's how I would actually produce that x value, okay? So, but I can think of this whole distance as being the number of intervals, number of complete intervals, right, times the length of each interval, right? And this works because the intervals are all the same length, okay? So I can make it like that because all of the intervals are the same length. Are we okay with that so far? So this product at the end here is just keeping track of the total distance from the starting value to the ending value that I'm looking for. That's how we, right? So if I have this distance and I add it to the starting value, then I get to where I want. It's the same exact idea as new y equals old y plus change in y, right? That's what we're doing here. So new x equals old x plus change in x, okay? Only I'm breaking down the change in x to look like number of intervals times the length of each interval. Is that good? Okay, so then, well, the cool thing is I've given the starting value a name, right? I called it A, okay? The length of each interval, we know, that's delta x, okay? So that's the second piece. But this number of complete intervals, okay? This is where my question at the bottom of the screen comes into play. What on earth does figuring out the number of complete intervals have to do with stuff that we've learned at the beginning of the semester? Well, if I want to know the number of complete intervals related to like what was actually given to me, so what was actually given to me was, again, this starting value, the length of each interval, and the current x value, okay? And I'm trying to figure out how many complete delta x intervals fit within the space between the starting value and my current value. Does that remind you of something? Yeah. Yeah. Exactly, right? So haha, this is why we did it, right? Okay, so we learned all of that specifically to be able to say, hey, I can figure out how many delta x lengths fit inside of the total length between the starting value and the ending value. And I would do that by taking this whole length. So how could I represent the whole length between the starting value and the current value? Current value minus initial, okay? And I want the relative size of that. The relative size of that with respect to delta x. So I divide it by delta x, okay? So again, reframing it in the way that we built up at the beginning of the semester, this quotient is saying if I measure the distance of x minus a in units of delta x, it's going to spit out a value. And that value is how many delta x's fit in here. Okay? So if I look at that for this starting value and this current value, I've got about well, maybe I should do it like that, but I've got, what? I've got 1, 2, 3, 4, 5, 6, 7, and some more, right? So I've got 7 and maybe about like 7.7, right? Delta x's, right? But remember, I didn't actually want like the exact number of delta x's that fit in. I wanted the exact number of complete intervals. So the way we take care of ignoring this extra little bit here at the end is introducing what's called the floor function. Okay? And that precisely does to the number that comes out here. So x minus a divided by delta x, right? That spits out a value. And what the floor function does to that input is it spits out the integer value that's, closest to the number given, but less than, okay? So in this case, the floor of 7.7 would spit out 7. Yes?
For like when we're using graphing calculator,
yes.
If you have a PC, how do you do the delta x
You're gonna have to define a string and just do like dx in graphing calculator instead of using the delta symbol. Okay. And then since we're talking about graphing calculator for a moment, if you just type the word floor into graphing calculator, it automatically introduces these symbols and then puts your cursor inside so you can type whatever you want inside of it. Uh-huh. Yep. So the floor of 7.7 is 7. The floor of 0.3 would be what? 0. The floor of negative 1.6 would be what? Ah, negative numbers are tricky. What's the floor of negative 1.6? So this is why it's a little bit dangerous to think about the floor function as just chopping off the decimal, because that's not actually what it does. What it does is it spits out the largest integer to the left of this value. Okay, so the largest integer to the left of 5.7, or sorry, 7.7. Oh, well, this is confusing now because I'm looking at different things. But the largest integer to the left of 7.7 is 7. The largest integer to the left of 0.3 is 0. The largest integer to the left of negative 1.6 is negative 2. And of course, when I'm saying to the left, I'm thinking of a number line. Question?
So they said when you're looking for piecewise functions in a graph, you can look at the endpoints on the left and the right, and the right and the right.
Yes.
How do you deal with the ones on the right and in the middle?
We're getting there. Good questions. Okay. So, but what I want to make sure before we move on to mid and right is that these are making sense. I want you to be able to explain to me what every component of this expression is that I just wrote down over here. Okay, because what we've done is we've actually defined a function, which we're going to call left of x. Yes? Okay. The x is the, yep, an actual current value of x. And the a is wherever we started to partition our number line. Okay. So a and delta x have to be given to you for this function to make any sense, right? Huh? So I'm on a function notation kick right now. Okay, so technically, as written, if I don't tell you what a and delta x are, how many unknowns are there in this function? 3, right? So if I wanted to, I could actually define left of x, a, and delta x like that, and then actually go through in graphing calculator and mess with a and delta x and be able to have all kinds of fun. Is that making sense? Okay. So, so having, if you wanted to get really fancy in graphing calculator and play around a lot, you could do this, and then that way, anytime you change the value of a or delta x, the function would still reflect those changes. Okay. Otherwise, you just have to go in and manually change a and delta x every time. Okay. That's lame. Okay, so doing it with the left endpoint isn't the only way. Okay, and so this is something that you're gonna work on for your Friday homework. But so let's just recap, right? So left x, what does it do? It takes the current value of x and it reassigns it to the left endpoint of the current value, of the interval containing the current value of x. Okay. So it reassigns the current x value. Now, here's the definition, right? A notation that you're going to see in your reading, and I'll probably end up switching to it soon because it's a nice shorthand, is to just say x sub L to mean the output of this function. Okay. It's just a convenient shorthand. Okay, so if this is what we know about left of x, what would right of x do? I'm going to stop talking now. You can answer this question. Let's see. We're at Caesar? Are you here? You have an idea? What would right of x do? Okay, yeah. So it would take the current x value and reassign it to the x value that is the right endpoint of the current interval. Okay? That was the easy question. How would we define right of x? So I want you to actually talk about this with your neighbor, and I'm gonna throw two things out there. You could work hard to come up with an answer, or you could use something that we've already worked hard to achieve to come up with an answer. Okay? So take a minute, keep that in mind, and try to come up with a definition for right of x. Yes? No. Wait, I don't think I understand the question. What do you mean? Delta x doesn't have to be 1 for the floor function to work. No. It will always produce an integer value. Okay, Moises? Were you here? Moises? Yeah. Do you have an idea? You add the, well, you add the a. Where do you mean? Oh, inside of the floor function? So, okay, so what did this mean again? What was the meaning of this? Actually, what was the meaning of just x minus a? Why did we use x minus a? Anthony, are you here? What was x minus a? What did that represent? So current value minus starting value, but what does that actually represent? Elena? Oh, Moises? Distance. So the total distance between the current value of x and the starting value of x. And then we divided it by delta x. Why? What's the difference between x minus a and delta x?
Yeah, isn't x minus a like your current x minus your initial x? And isn't delta x change in x?
Okay, so that's a reasonable question. So x minus a is representing a change in x. Okay, but the value actually changes because x is allowed to vary, right? So x can change, right? So this is not a fixed amount. Whereas at the very beginning of the whole situation, I said delta x should equal 0.8. So delta x is a constant value in this setting. It's the interval length. Okay? Good question. So let's revisit. So x minus a is the total distance between the current value and the initial value. Delta x is the size of the intervals. What was the meaning of the quotient? The number of delta x lengths, yeah, which is the number of intervals. But then we took the floor function so that we would have the number of complete intervals, right? Because just the quotient could spit out the number of the number of complete intervals plus a little bit, because it could be more than, 5 intervals. It could have been 5.5 intervals, right? So that's why it's important to pay attention to meanings, guys, right? So I can't just change the x minus a to an x plus a, because that's no longer representing the number of intervals anymore. So remember, this whole piece, represents the number of intervals. Yeah?
So I'm thinking that with this, as far as like how to define one to the right,
Mm-hmm.
we either have a function that we shifted to the next whole value,
Right.
or we could take the current one, which is the left,
Okay.
and what that gives us is the left value, and then could we get to the next value by adding one delta x value?
We sure can. Okay. So remember, left x spits out the value to the left of the current x value, right? So if I want to get from here to here, right, then I can just add a length of delta x. Yeah? Ruby? The harder way would be to change the number of intervals, right? So right now, this is the number of intervals, complete intervals, not containing the current interval. So if I wanted to include the current interval, right, then I would have to increment this by 1. Okay, so I would have to, an alternative would be to say a plus, and it just looks gross. We did so much work. Why bother? But we'd have to increment by 1, right, to say these are the number of intervals to the left of x, but I want to include the interval containing x, so I'm going to add 1 and multiply by the length of the intervals. Question?
Is there a ceiling function?
There is a ceiling function, and it does exactly what you would think it does. Which is what? Yeah. Okay. So, all right. I'm going to erase that because it's way too much work. Okay, so what is the next question going to be on this slide? What is mid? What does that do? That's a question mark. What would mid x do? Yes?
Would it be like the left x plus the right x divided by 2? Plus the left x plus half x, or half x.
But what does it do? It gives you the midpoint of the interval containing the current x value, right? All of those words are important. All of them, right? Because you could be talking about the interval way over there, but my x is right here. Okay, so mid x will take the current x value and reassign it to the x value that's in the middle of the current interval containing x. Okay? And oh, I erased stuff, so sorry, it looks funny. But so if we wanted to define mid of x, right, that would look like, if we're not trying to work too hard, I think I heard it, take the left value, and how much do we need to increase by? I heard people say half. If I write 1/2, is that correct? Half of what? Delta x. Okay. Groovy? Sweet. Okay. All of that work was for a reason. Okay? Because notice, all we have done so far is take x values and reassign them to other x values. We have not created a function yet that will give us rate of change. Okay? All we've done is reassign current x value to a different x value that we like. Okay? Now, why did we do all of that? Well, because the big picture, again, was to define a step function. Okay? We're going to call it step of x. Okay? That's my easy way of saying a piecewise constant rate of change function. Okay? And I want my piecewise constant rate of change function to reflect the actual rate of change given to me in this current scenario. Okay? So here I've got, in blue, an actual rate of change function. Okay? And I've chosen to create a pretend rate of change function in pink. Okay? And how did I create it? I put, what did I do? Uh-huh. Okay, so we create this step function by taking current values of x, reassigning them to the left endpoint, finding the actual rate of change value using the blue graph, and then taking that value and making it the value for every x in the interval. Okay, that's what we're doing here. Okay, so that's the process. Holy moly. Okay, so how do we encapsulate all of that? Okay, so I'm defining a new function, the pink function. I want to call it step of x. Okay, and so it takes in the current value of x. What's the first thing we have to do to it? So, okay, so let me rephrase. I've got an x value here. I want to know the corresponding rate of change for this x value on the pink graph. Oh, that's an ugly one. Hold on. We'll do it here. Okay, so I've got a current x value. Current x value. I want to know, how do I find the corresponding rate of change on the pink graph? Where do I look for that? Well, okay, sorry, that was sort of an ambiguous question. So the y value, right, of this point is the rate that I'm looking for. But how did we get that? Okay. What's the process I go through? Richet's making hand motions. Okay, so the first thing I do to my current x value is I feed it through left of x, right? And that sort of reassigns it to this x value. And then why would I do that? How do I get to a y value? What is the y value for this pink strip? Don't give me an approximation. I want an exact representation of the y value of the pink strip. So remember, left of x gives us an x value. Left of x puts us here. I'm trying to define step of x. I don't know what step of x is. The only thing I know is my actual rate of change function, r, which was in blue. This is what's given to me. Everything else in this picture I've created. Yeah.
Whatever your function was that made the blue line, put left of x into that.
Okay. So, oh, say it louder. R of left of x. So this value here, where the pink bar is, that is R of the left endpoint, right? And that is, in fact, the way we define our step function. Because any x value that I feed in, this function is going to feed it to the, push it to the left, and then say do R of that. So it's going to spit out a rate. Okay, so within this interval, for example, this current x value will be sent to here and then assigned to the rate that's down here, and so I'll have a corresponding point right there. Okay, and for this x value in the same interval, it's also going to get processed through the left endpoint, mapped to the rate, and then the corresponding point will live right there. Okay. The magic has happened. We have our piecewise constant rate of change function. It's called step of x, and this is how it works. Okay. R was given. R is the actual rate of change function that was given in the beginning of the problem. So with the bouncing ball thing, right, the ball going up and down, it was a given rate of change. Okay. So the whole setup, the big picture is that we are looking at a scenario in which we're given an actual rate of change function, and we're trying to get to an accumulation function. Oh, that's the big picture, right? And so how do we do it using the tools we have? Because our actual rate of change function could be really pretty looking, right? And we only know how to deal with things that look like steps, okay? That's where we're at. So if we have constant rates of change, we know how to get from constant rate of change to accumulation. So that's why we're taking our actual rate of change function and creating our sort of approximate rate of change function, which we're calling step of x. Okay. So, but again, the big picture, the whole reason we do this is because we can get accumulation from rate. Okay? And we do that by saying little bits of accumulation occur, right, by doing rate times little bit of changes in our input. Okay? So little bit of accumulation plus little bit of accumulation will give me total accumulation as I continue to add up the little bits. Question?
So with our calculators and things like that, like how hard is it to do a little bit of change of like 1,000 or whatever?
Not hard at all. It's a beautiful thing. And starting on Friday, we're going to really get into how we can use graphing calculator to make this just a really pretty process. Okay? But in order to use graphing calculator, we have to understand what everything means and what the notation looks like, because that's the way that we communicate with graphing calculator. Okay? Is that a stretch? Okay. All right. So all of these these terms are representing little bits of accumulation. Okay? So R1 delta x is a little bit change in y, right? Change in y1 plus change in y2, and so on. Changes in y, not y values. Okay. So all right, so let's really analyze this. Let's just drill this in. So what kind of function is implied by the blue curve? What's the input and what's the output? So when I say what kind of function, when I ask that question, I'm talking about, are we looking at a rate of change function or are we looking at an accumulation function? We're looking at a rate of change function. So what's the input? X, right? Whatever that represents. And the output is the rate at which some quantity is changing with respect to X. Okay, so I haven't given you variable names, right? I haven't told you what X represents. I haven't told you what Y represents. Okay, but there are two quantities implied anytime you look at a rate function, right? Because it's a rate of change of one quantity with respect to another. Okay, so so there's some quantity Y. Maybe it represents distance. Maybe it represents work, something, right? Okay, and this function is showing the rate of change of that quantity with respect to X at any given moment in time. Okay. What kind of function is the pink step graph? Let's see. Taylor J, are you here? Taylor J? Joseph? So it is a step piecewise constant rate. Constant, what kind of function? Rate of change function. The pink graph is still a rate of change function, okay? Because it's still inputting X values and outputting rates, right? Because remember, the pink graph comes, the step graph comes from the rate of change function. That's how we get it, okay? So it inputs an X value, it outputs a rate of change. Is it the rate of change of the current X value? So this one is taking, so you can see up here, right? The intervals are here to here, here to here, right? And it's taking the midpoint of each interval and assigning the rate of change that way. So, so if I wanted to define this step function, it would be what? R of mid X. Okay. Why do we create it again? Ruby? Are you here? Ruby? Yeah. Why do we create it? Okay, well, so it definitely gives us the rate of change at the midpoint of every interval. Taylor Shackelford, are you here? Yeah.
Created to, like, it shows like the accumulation over the entire R length.
So it doesn't show us the accumulation, but it definitely gets us closer, right? Because remember, the pink graph is showing rate of change. The pink graph is not showing accumulation, but it's giving us rate of change that's constant. And if we have constant rate of change, we know what to do. Promise. You've learned it and you've showed me, okay? So that's why we do this, okay? So we've already actually broken down some of the particulars. We've already said that this step function is created using the mid, right, the midpoints, okay? We could also talk about the fact that this starting value is at a equals 0, and the other particulars would be that the delta x's, right, the size of the intervals are, I think it's 0.3, okay? So when it asks for describe the characteristics, these are the characteristics over here, okay? So, so just to really hone that in, right? So if we look at the third interval, 1, 2, 3, so here we are, okay? How was its constant function value determined? How did I get this value up here? Courtney? So we took the midpoint on the x-axis and then did what? To the y value of, well, so the middle of the interval is the x value. Let's see, Sarah, can you help out? So we're at the midpoint of this interval. How do I get this constant value? Where does that come from? No. Lauren? Are you here? Lauren? So this is mid-x, so we've done that. We've gotten to mid-x. How do I get this y value, though? Yeah? Which graph? On the rate of change graph? There's two rate of change graphs. The blue one, okay? So we take the value on the blue rate of change graph at the midpoint and assign that value to the entire interval. Okay? That's where we're at. So we got some more to do. Okay, so we'll pick this up on Friday. You've got some really good reading. So do that, and the homework assignment is going to really just give you the opportunity to get all of this totally under your belt.